This is the first of two presentations on pH, pKa, and the protonation state of water. So let's go through some definitions. And I have an equilibrium reaction where ammonium loses a proton to water and becomes ammonia, the conjugate base, and it makes the conjugate acid, which is H3O+. And so there's a KEQ for this reaction, and it's like the KEQ for any kind of reaction. By the way, that's an unusual one that I just told you. It's got water as the base, and that's going to be true for all of these. But in any case, in this KEQ, we can determine that quantitatively by multiplying the product of the concentrations of the products, which are the ones on the right side, and dividing that by the product of the concentrations of the reactants, which are on the left-hand side of the expression. So that's old KEQ. We can multiply both sides by the concentration of water, which is a number. It's 55.6 moles per liter, and so we're essentially just multiplying this by a number. And when we do that, we can eliminate the H2O's on the right side of the equation. So we're left with, on the right side, just the ratio of the the concentration of the conjugate base divided by the ratio of the acid times the H3O plus concentration. On the left-hand side, we have the concentration of H2O times KEQ. And again, this is a number. And recall that KEQ is a constant, so in fact a number times a constant is going to be a constant number. It's going to be a number. And so on the left side we essentially still have a constant. On the right side we're going to look at the ratio of the conjugate base, the concentration of the conjugate base to the concentration of the acid. We're going to look at that ratio. It's going to become very important in a lot of these conversations, and we're going to multiply that ratio by H3O plus. And so in any case, the concentration of water times KEQ, we're going to define that as the Ka. This is the K acid. This is an equilibrium in which water is the base, and we have an acid that's going to lose a proton to water to make hydronium, and it's going to make the conjugate base. So this is a Ka expression where we lose protons to water. We could take the negative log of Ka and the negative log of what's on the right-hand side of the equation, and the negative log of Ka we're going to call the pKa. So this is the definition. The negative log of the Ka is the pKa. And so keep in mind, as the KEQ gets larger, the KEQ gets larger, Ka is going to get correspondingly larger, and the negative log of Ka is going to get correspondingly smaller. It's going to become a smaller number. So in any case, we have the pKa is the negative log of the ratio of the concentration of the conjugate base to the acid times the H3O plus concentration. And let's recall that we can shift the equilibrium above. So I've crossed out the concentration of the conjugate base and the concentration of the acid in the expression above, and I want to show you what I mean by that. In the above expression, we can shift the equilibrium by changing the H3O plus concentration to hydronium. And so that means as follows. Suppose we increase the H3O plus concentration. Well, Chap02 says we're going to shift the equilibrium to the left. In other words, we're going to make the ammonia more dominant, and the water actually is not going to become more dominant. In these particular kinds of reaction, the water is in very high concentration and the acid is in very low concentration. And so we essentially say that the water concentration remains constant. So if we shift the equilibrium to the left, really what we're doing is we're increasing the NH3 plus concentration. And so we can shift the equilibrium to the left by increasing the H3O plus concentration. We can shift it to the right by decreasing that H3O plus concentration. We can shift these in either direction. Well, let's shift the H3O plus concentration such that the conjugate base concentration on the right side is equal to the concentration of the conjugate acid, which is on the left-hand side. If we shifted the H3O plus concentration such that those two are equal, then on the left side of the bottom expression that I'm showing you, we have pKa equals, and then the rest of that negative log of Ka equals negative log of that expression. If the conjugate base concentration equals the acid concentration, now those cancel out, and so that equals 1. So now we have the negative log of H3O plus only, which is by definition the pH. And this becomes really important. The pKa equals pH when the acid concentration is the same concentration as the conjugate base. When those two are 1-to-1, pH is going to be the same as pKa, and pKa is going to be the same as pH. And so we're going to use this. It's going to become very important as we analyze the protonation state of acids in water. So for definitions, recall that pH is defined as the negative log of H3O+, and it's a measure of the acidity of a solution, of an aqueous solution. That's very important. And as the concentration of H3O+ goes up, the pH goes down. As the concentration of hydronium gets lower, the pH goes up. So for all of these expressions, KEQ is a constant, and Ka is going to be a constant as well. It's not going to change. Most students incorrectly say that if we change the H3O+ concentration, for example, in the far above expression, that we're going to change the KEQ. We are not going to change the KEQ. The KEQ is going to be constant. It is an equilibrium constant, which is why we call it that. So we're not going to change this, but we will change the rest of the compositions. And we'll talk about specifically how we'll do that, not in this one, but in the next one. So the equilibrium can be shifted in either direction by adjusting the H3O+. Le Chatelier says that the pH is going to have an impact on the ratio of the acid to the conjugate base, and that's the inverse of what I have above, but you could say that's the ratio of the conjugate base to the acid above. That ratio is going to be influenced by the pH, because the pH is the H3O+ concentration. And as we've suggested, we change that. We can change the ratios of the conjugate base to the acid. So we add H3O+, we're going to shift the equilibrium to the left, and NH3+ is going to be more predominant. If we add OH-, then we're going to shift the equilibrium to the right, and the conjugate base, the RNH2, is going to be more dominant. pKa, by definition, is a measure of the acidity of a compound in water. This is the same type of competition we have above, where we have an acid that's competing to lose a proton to water to make the conjugate base and make hydronium. You should think about this as a competition. The acid is trying to lose a proton to push the equilibrium to the right. The hydronium is trying to lose a proton to push the equilibrium to the left. This is a competition between two acids trying to lose a proton. And often we talk about this as a competition of two bases trying to grab a proton. But I like to talk about it as the competition between two acids. So the pKa is a measure of the acidity in water. The lower the pKa, the more acidic it is. And pKa, by the way, is the negative log of H2O, concentration of H2O times KEQ, as shown above in the equations. Lower pKa, higher acidity. And the lower pKa indicates that the acid-base expression as shown above, where the acid is losing a proton to water, is going to be more favored to the right for compounds that have lower pKa's, that is, for compounds that are more acidic. So let's go forward a little bit. We have the same expressions. We're losing a proton from an acid to water, and we're going to make the conjugate base and the conjugate acid. We have a KEQ expression. We multiply both sides by H2O. This is all what we did on the last slide. We cancel out the concentrations of H2O. We define the Ka as an equilibrium where the acid donates a proton to water, and the Ka equals the concentration of water times KEQ. So that's going to be Ka is going to be a constant as well, and it has the formula of that ratio that's shown in the fraction above. We take the negative log of Ka's, and we have now the negative log of the expression at right. The negative log of Ka is defined as the pKa, and what's going to be important for us is that when the pH equals the pKa, the acid concentration, that is the acid on the left-hand side of the above expression, is going to be the same concentration as the conjugate base on the right. So when the pH is the same as the pKa of the acid, then the acid and its conjugate base are going to be in equal amounts. And this is going to be true, vice versa true. If the acid and its conjugate base are in equal amounts, that means that we're at the pH which is equivalent to the pKa. And so in the above expression, we have an ammonium acid. The pKa is around 9. So at pH of 8, this is what the above expression means. At pH of 9, the ammonium concentration is going to equal the amine concentration. And so let's look at another type of reaction so that we can use another example. This is acetic acid in water. Acetic acid is going to lose a proton to make the conjugate base, which is the acetate at the right, and hydronium ion. Again, for all of these, water has to be the basis when we're talking about these. These are acid-base reactions in water. And so at the pKa of a 5, which is the pKa of the pKa of the acetic acid is 5, so at pH of 5, the acid and the conjugate base are in the same concentration. Therefore, the concentration of the acetic acid is equal to the concentration of acetate. And for the reaction of phenol in water, a little bit different. The pKa of phenol is 10, and therefore at pH of 10, we have half phenol, half phenolate, that is the conjugate base of phenol. And so we're able to tell at what pH the acid and its conjugate base will be in equal amounts by just saying at pH equals pKa, the acid and the conjugate bases are identical. We're going to learn in the next slide presentation what happens when the pH does not equal the pKa, and so you can analyze not only which direction is shifted, but by how much. So in other words, going back to the expression at the very top, for that one, pKa of that acid is 9, so at pH of 9, we have an equal amount of the ammonium on the left and the conjugate base, that is the amine, on the right. What happens when we increase the acid concentration, the H3O plus concentration? We're going to shift the equilibrium to the left according to Le Chatelier, but we're going to use the above expressions in the next slide presentation to talk about how much this is shifted. And so let me give you a summary at this point. Number 1, KEQ and Ka do not change with changes in composition, and the Ka is the same as 55.6 times the KEQ. That's the concentration of water times KEQ. The equilibrium of the acid reaction with water can be shifted to the left or right depending on the pH. Because H3O plus is one of the components in this reaction, we can increase or decrease that and shift the equilibrium to the left or to the right and analyze this by Le Chatelier. So pH by definition is the log of H3O plus, the concentration of H3O plus, and this is a log scale. So if we lower the pH by 1 unit, that means we're increasing the H3O plus concentration by a factor of 10. And if we increase the pH by 3 units, this is the same as decreasing the H3O plus concentration by 10 to the third, or by decreasing it by 1,000. So the acid and the acid concentration, the conjugate base concentration, are equal when pH is the same thing as the pKa. And when the pKa equals the pH, we know that at that pH, the acid concentration and the conjugate base concentrations are equal. So these things work vice versa. In the next presentation, we'll see how we can use the above analysis in order to predict the protonation state of molecules.